In this video, we are going to work with some Taylor series, specifically Maclaurin series, to create new Maclaurin series for new functions. So, in particular, we're going to be concerned with these three Maclaurin series. So, in a previous video, we've developed the power series for e to the x, sine of x, and cosine of x. So what we want to do now is combine these already known Maclaurin series with what we know about properties of power series to create the Maclaurin series for some new functions. So let's get into the first example to see exactly what I mean by that. So we have f of x is equal to the cosine of the square root of x. Well, that's very similar to the cosine of x. So we're going to start with the Maclaurin series for the cosine of x. And then we are going to apply the properties of power series to find the cosine of the square root of x. So all we have to do is we take out the x from our Maclaurin series, and in its place we put the square root of x. And then simplifying that, the square root of x to the 2n, we have x to the n. It simplifies to x to the n. And that's it. For this particular function, the cosine of the square root of x, this is the Maclaurin series representation for that function. That's all there is to it. Now, the next thing to do would be to write out the first 5 or 6 terms of the Maclaurin polynomial. And that's what we have here, is I went out and determined what the first 5 terms of the Maclaurin polynomial are. Now, let's see exactly what we mean by the cosine of the square root of x being equal to this Maclaurin series, or being equal to this Maclaurin polynomial. And to do that, let's go to Desmos. So in Desmos here, I graphed the cosine of the square root of x in red. And so what we want to do is we want to see how the first term of the Maclaurin polynomial compares with that. Well, when we look at this, they're only in agreement at one spot, which is at x equals 0, which is where the Maclaurin series is centered. Remember, power series always converge at the center. In this case, the center is 0. So convergence is at 0 and only at 0 in this particular case. But when we add 2 terms to the Maclaurin polynomial, well, it looks like this polynomial, 1 minus x over the square root 2 factorial, is in agreement or converges over a little bit further, a bigger interval. When we add the third term of the Maclaurin polynomial, we can see that there is a greater convergence. The fourth term of the Taylor polynomial, even greater convergence. And then finally, the fifth term of the Taylor Maclaurin polynomial, we get even greater convergence. Trying to get rid of that last. There we go. Even greater convergence. So you can just imagine as we add more and more and more terms to the Maclaurin polynomial, we're going to get convergence over a larger and larger and larger interval. Well, we could go to this problem and we could determine what the interval of convergence is for this particular Maclaurin series. That's something that we know how to do using the ratio test. What you would find out is that the interval of convergence is infinity, that it will converge over all values of x as we let the Taylor polynomial approach infinity. All right, that's it for this particular video. I will be doing more videos with some more of these problems.